Okay, so our tool's a Forge. This is the integration of our debugger, DDT, our source code profiler map, and our application profiler performance reports. And all of our tools are designed from the ground up, both architecture and user interface wise, to be optimized for HPC codes, particularly kind of traditional SPMD type of codes where you're using something like MPI for distributing a lot of processes and decomposing data. Supported on all major architectures, AMD, ARM, NVIDIA. We've actually added support for ROCm GPUs in our latest release, and used it a lot of top 500 sites. In all fairness, today, most top 500 sites that are doing HPC, especially SPMD type of traditional HPC, are using our tools. Designed for ease of use, especially in profiling. Debugging, there's not a lot of solutions, but in profiling, there's a lot of great tools out there for performance engineering. They range from extremely sophisticated to a little bit simpler to use. And for our source code profiling, we've really tried to focus on scalability and ease of use. Very, very easy to bring the tools up and quickly be efficient. Our debugger today is about performance engineering, so I won't say too much about it, but these are just a few of the highlights of some of the strengths in our debugger, and in our next session, we'll be focusing on that. So performance tools, and I like to prefix the performance discussion with a little bit of discussion about methodology. And I think this is really important that I get a chance to work with a lot of customers that are analyzing their codes, and too frequently I see issues of folks will say, oh boy, I've got like a vectorization problem or a memory access problem, and we have a first look at the code and there's an IO or an MPI problem. This is really important to make sure that at every iteration, every time you rebuild, you also do a regression test for performance, because errors in IO and communication can be orders of magnitude size problems, where at the CPU level, it's more like factors. And so there's a little illustration I use just to kind of like following the correct steps. Now, obviously, correctness is really important. It's become pretty easy to introduce regression testing for performance into your CI, and I really encourage that. So every time you're modifying the code, doing check-ins, verify that performance issues are correct, and that going back and fixing that can take a lot. So step one, verify correctness, and then get a high level picture of performance, make sure the IO and performance is correct, and then kind of piece by piece work down the roadmap here of improving performance. So in our tools, kind of the first step is performance reports, and we'll go through some samples of this, but it's essentially a one-page high level report that shows you the application, the nature of performance in the application. Not just for developers, but also for kind of like system owners. So for example, if you're looking at getting a new system, or you're going to add to your system, or you want to modify it in a certain way, performance reports is a great tool to get a high level picture of how applications are going through. Then kind of the second step is our source code profiler map, and that's going to be a large focus of what we're working with today. And these are just a few of what I see as kind of some of our strengths or best features. Finding memory usage, and this is kind of fun one that traditionally things like memory leaks and understanding memory usage is kind of viewed as a debugger type problem, whereas in the source code profiler, it's really easy to see where memory patterns are changing and spotting memory leaks, that type of thing. Imbalance problems, especially in MPI, as I mentioned, kind of early step on the roadmap. This is one of those areas, especially when you're with new codes or you're making significant changes to introduce significant problems in MPI and IO, and seeing those, understanding those in map is really easy. Understanding OpenMP usage, and we'll go through some examples of showing multi-thread, multi-process type applications, and being able to see that you're distributing the workload across your thread bank. Improving memory usage, and obviously my chart here is kind of following the performance roadmap step by step of the pieces that you need to optimize kind of in order. Just a high level view on map, and I'm going to be spending some time with this, so I won't get into too much depth, but kind of the main points of significance with map is both the user interface and the architecture are very scalable. We run the tool on thousands, tens of thousands of processes, and both the interface and the way the architecture works is highly scalable. And the way we run map is it's a sampling profiler. So a lot of the high power tools I mentioned are instrumentation profilers, where you modify your code to enable the profiler to get information on segments of your code. Map does this through sampling. So we use a sampler that runs starts out at the order of 50 hertz. And at each cycle, it gathers information for about 30 or 40 various metrics. And a key part of that design is, as the program progresses in time, we resample the data onto a new time base and then decrease the sampling frequency. And for HPC codes, where it tends to be, big chunks of computational work, this sampling technique gives really high fidelity of how time is actually being spent across your processes. Very low overhead. So the run itself typically is less than 5% during the runtime. One caveat I'd like to mention, especially when running to scale, is at the end of your application, when your application exits, the profiler still needs to gather up all the data and integrate the data across all the processes. So when you're first starting out, give a little bit of extra time. If your application takes 59 minutes and you only have an hour allocation, there might be issues of things dropping off. And if it exits, you're going to lose the data on that. So until you get a feel for the integration time in your application, give it some extra. Python. So yeah, we've especially in this release, we've added a lot of support for Python. For the most part, most things that we support in C and Fortran are also supported in Python. Now, obviously, as an interpreter, everything that you would do in a debugger or a profiler don't exactly make sense, but it's really complete. We put a lot of additions in on this release to support Python more additionally. Mainly focused on SPMD, MPI for Pi. With performance reports, we've done some additions where I think it's also going to give some interesting information on ML framework type of applications. Things like TensorFlow and PyTorch use a very different architecture. They tend to be task-oriented threading models. That's not exactly how map works, but in performance reports, it'll give you a high-level interpretation, at least, are we spending a lot of time in I/O or MPI, or are we spending the bulk of our time in the computation on the GPU, ideally, as we should. So we do support GPUs. Sounds like you don't use GPUs much, but we fully support CUDA and ROCm as of the current release. Okay, so with that, I'm going to pass it back to Eva to give an illustration on your machine, and then we will go with some demos. Eva, Tony, you there?
Tony's here.
All right, Tony, are you going to kind of lead the how to do it on your machine part?
Looks like it, yeah.
Okay, great, thank you.
Let's, oh dear. I don't know. How do you?
Should I put the slides up? Or
What? Yeah, okay. I got no idea. Well, I've got more than 2 desktops. It's only showing 2. Well, let's try this, see what happens. Oh no. What's it doing? Share screen. Sorry, my Mac is being a big pain.
Permissions issue.
Yeah.
That one, you have to restart the Zoom, unfortunately, after
Yeah,
you enable.
I know. Yeah. I'll be back in a moment.
Yeah, thanks. So it looks like we have to wait a few minutes. Yeah, maybe in the meanwhile, I can talk about what we have on Ookami. So we have the Forge toolchain installed. Like it's a module, so you can just search for the Linaro model, and there are two versions currently, the latest one and the previous release. And that it's licensed, and we have like 16 seats for the license. So you can run 16 processes, and starting the GUI also works on Ookami, but it might be a little slow. So there are better ways to do it, and Tony is about to share them right now. Perfect. Thanks.
I've got unmuted again. You can see the slides, and it's the slideshow. Come on, slideshow. Is the slideshow working?
Good,
Yes,
yeah,
sir.
I got it.
Yeah, okay. Okay, so I'm just going to do a quick walkthrough on how to use the remote client on Ookami. So as Bo has already nicely pointed out, there's basically three parts to the Forge suite. There's a high-level overview tool called Perf Report, and then there's a debugger and a profiler. So DDT, as Bo mentioned, will be the next topic in the next webinar, and today we're looking at map. I'd just like to point out, when I wrote this, I didn't know which order it was going to be, so I may be showing you DDT, but it is all pretty much the same thing. They will have the same kind of dialogues for interaction. Since I don't work for Linaro, I can tell you all the dirty details. So Forge was originally created by a company called Linaro that was bought by ARM, which is now in the control of Linaro. And you actually see some of these older names in the tools. Almost all of the history of Forge has been removed, so it's now all Linaro branded. But the configuration directory is still called .alinea for compatibility reasons. So you'll see that later on. And so don't panic if you see that and you wonder what that has to do with Linaro. So on Ookami itself, you can find Linaro tools via the module command. So you can say module available and then ask for Linaro modules, and it will tell you that there's an older version installed, 22.1, and then there's the latest version, 23.0. And if you just load the Forge package, you can then run the tool with the Forge command, or you can use the perf report command too. However, this can be a problem when you're running over secure shell, which of course you should be. Interaction with remote GUIs can be really, really slow and requires X11 forwarding to set up, and there may be local issues doing that. It's like configuring PuTTY or some other tool, and you have to tunnel over SSH connections. You can also use Forge tools from the command line, which is obviously very useful in batch jobs. So you can just walk away and let it collect data and then come back and look at the data in the GUI later. The other way of doing it interactively, which is much more responsive, is to set up a client that you install on your laptop or desktop or whatever you're using locally. So all the interaction is local to your machine, and it sends commands off to Ookami remotely. Again, this is all through SSH in the back end. And both of these usages integrate nice and cleanly with Slurm and other job schedulers too, of course. I believe Bo's earlier example had an LSF command in it. So there's all kinds of interactions that you can configure, and I'll indicate that in one of the later slides. So to install the remote client, it's really easy. There's two links there. It's sort of point and click and go, really, so it's quite easy. My main machine is a Mac, so I've installed it there, works fine. I've installed it on Linux on a Fedora system, it works fine there. And one of our students was brave enough to try it on Windows and it worked there for him too, so it's all good. And so all the examples here are from a Mac, but you know, it's all much of a muchness, as the English say. It's all the same. Forge is a license suite of programs. You don't need a license for the remote client, so you know what you install locally on your laptop is not licensed. But there are license restrictions on Ookami for the actual usage of the tools. And there are various different parameters you can have for the number of users, number of seats, size of programs, and so on. And we have a fairly modest setup at the moment. And we're going to reevaluate after these webinars in case, you know, if there's a sudden burst of interest in these tools, which we hope is the case. So once you've installed it, you run the application locally, and this nice GUI window pops up. And you can see down at the bottom here, there's a remote launch option and a menu below it where you can configure different connections to different machines, for example, or different kinds of connections to different machines. So there's many options you can have in there. So you click on that and you could choose configure. Now you need to know some information before proceeding. So when you load the Forge module on Ookami, you need to understand where the software is installed, so you can do which Forge. And so therefore the installation area is that path. So it's software installed under the global file system for Linaro and the particular version of this software. So the window that pops up for the configuration, then you can configure a connection name, the host name, which includes the standard secure shell style, just a host name, so like login.okami.stonybrook, or you can use username at in the same SSH fashion, which is, well, that's basically what it is. So there's the remote installation directory, which we just saw. I have a remote script, which I've put in this location, and I'll explain more about what that does in a moment. You can set up private keys to enable more automation of the login. It still goes through Duo, like any other login on Ookami would. And I have proxy through login node set, which seems to help. Okay, so what's this remote script thing? So it's basically like having a login session. So when you log in, certain things happen. And when I show you the remote script, I'll go through what those are. You can have any number of them in any location you want, that you can write into, of course. And so you can have different config files in the remote scripts that set up different kinds of jobs. So you might have some jobs that involve, say, Fujitsu MPI, or something involving GNU and OpenMPI, or something with MVA pitch and Cray. So you can set up different scripts, different configurations in the tool, and configure the one that you want. And each time you connect, you'll get hopefully the correct configuration. So here's what I did and got working. So here's the file that we just referred to a moment or two ago. So these first two source commands are basically mimicking an interactive login to Ookami. So they set up access to all of the global modules and your own personal setup, for example, your own module files or environment variables and so on. And then we set up the environment for this job. So this particular remote script, and again, I could call that anything I want. I could call this like the Fujitsu configuration script or something. So I'm loading up the Fujitsu compiler, and of course, I also want to load up the Forge tools. All right, so once the connection is made, this script is sourced, and so then it acts as if I'd logged in and typed these commands, well, typed in the last two commands. The first two are handled automatically by the system. When I go to run a job, for example, I'm running a simple MPI program, So the example I used was just a pi approximation program. That's the somewhat famous one that was in the that is in the MPI-CH distribution. So I can select MPI. I can configure MPI to have as many ranks as I need, split across number of nodes in various different ways. The Forge tools support various different kinds of MPI implementations. And for Fujitsu, well, Fujitsu is based on OpenMPI, but it's not quite OpenMPI. It's sort of a completely mangled version of OpenMPI. So OpenMPI compatibility works for Fujitsu MPI. If you're using the ordinary OpenMPI, you would just use OpenMPI. And then you select Submit to Queue. In other words, go through Slurm. And you can set up parameters, for example, the maximum runtime for the job. So as Bo mentioned, when you're doing profiling or debugging, often there's some overhead. So the time you had for the bare run of the program might not be sufficient. So you can configure that there. And then the queue, which is equivalent to a Slurm partition. I'm just using short because I'm doing a really small demo run, and I don't need to run more than a few seconds, a few seconds basically. And then in configure, you can select a template, or you can create your own template if you know what you're doing, that matches the job scheduler on your system. So I just selected the Slurm template file, and that works fine. So that's just telling Forge how to recognize job numbers and the commands that it uses for submission and canceling jobs and other things as well. So I do all of those things. It's quite simple, and I just click submit, and then the program runs, and I get a nice little GUI pop up, a new window, and this has got all of the source code in it. So you can see all the source code here on the left. There's different frames for the source code, and you can look at the variables that are available. You can see at the top here against all, there is 0, 1, 2, 3, which are the 4 MPI ranks that I selected in the program. So there's 4 MPI ranks. And then you can go look around at all of the parts of the program, look at watch points and breakpoints. You can do tracing. You can rerun the thing, put in breakpoints, say run up to line 32 and then stop, and then you can click on variables and see what their values are, for example, which is really helpful for inspecting programs. So, you might detect that the pi on one process is 0 when it should be, 0.8 or something. So before being merged into the final answer. So that's how you use it. And I mentioned this. So for the Fujitsu MPI, you want OpenMPI compatibility. You can use that on command line with this command, this option. So that's minus or dash MPI equals OpenMPI compat. For MVAPITch2, it has a very tight integration with Slurm, so you can just use Slurm, and everyone's happy. And that's that. And if anyone's still awake, are there any questions?
Thanks, Tony. I think that was great. So everybody should be able to use it. And also there is also the option to run it without the GUI in case you don't like that. You could just do like load Forge in your shell, and for your job that you submit, just put map -- profile in front of the whole command that it's running the application. So you don't have to open the GUI, and it will just produce a profile file, which you can then load later on in the GUI, if that's what you prefer. So there are several ways to actually handle that.
If there's time and interest, I could be very, very brave and try to do a live session.
Whatever you think, Tony. I forgot about the notion that we were going to have an opportunity to look at map files. And so our budget now is a little bit bigger. So I know that I asked that, but maybe we just leave it as if anyone has questions, they can connect directly with you and Eva if they have problems from what you've shown already. Is that maybe fair?
Yeah, sounds good.
Okay, let's do that, because if folks have some map files to look at, that's always one of the most fun things to do. So yeah, on questions, there's not a whole lot of us. So if you have a question, don't hesitate to unmute and interrupt us. If you prefer not to, go ahead and just type questions in chat and we can broker those through that. Otherwise, I'll share my screen again and we'll get into some actual kind of hands-on demos. All right, you getting my virtual machine?
Yep.
Yeah.
All right. So this is going to be a little embarrassing. One of my main responsibilities is to work with clients to make sure everybody is up to date with the latest version. And when I went to update myself last week, I'm having problems with my VM, so I'm still using the old version. But functionally, pretty much everything I wanted to show is the same, so that'll be fine. But I feel ashamed of not having all the new logos and such. So as Eva mentioned, you can either run the tool interactively or through the batch system. Pretty much for most cases, I encourage running through your system, whether you're running on the command line or you're creating your profile through the batch system, especially for somewhat larger runs. The workflow is just a lot easier of create your map file at your convenience, come back and use the interface to do it. Also, it's a little easier to script up a whole bunch of different runs. So you might want to try different configurations of how many processes per node, how much, certain memory nodes, threads per process, all those kind of permutations that you'll be doing in performance engineering type of stuff. Just as a lot, you can script it up and get a whole bunch of batch files going that way. So actually, let me back up a little bit here. I mentioned I've really been trying to encourage using performance reports as kind of the first line tool. So let's start with that. So I have kind of a use case here that we did for analyzing various configurations of WRF on Graviton systems. And I'll open up all the test cases and then talk about what we did. So we essentially ran WRF on a Graviton 2 and then on a Graviton 3. And let's see, mount to porosity interface here. Okay, so we started with just the release build of WRF on Graviton 2. So let me just go over kind of what the output looks like. At the top, we have a summary of the run, includes the total time for the run, then a breakdown of how the time is spent. So the percentage of time in compute. And if you did have a GPU, it would include time for GPU. If this was part of a Python code, there would be a high-level summary of time spent in Python. And then just a little bit more detailed information on each of the high-level breakdowns. So some details of CPU metrics, time spent in MPI, IO, threading, memory, energy. This system did not have support for energy metrics, so we don't have that data. Also, it would have luster if we had luster, but we did not have luster on this system. So a very easy way to get this high-level picture of how time is being spent. Also, one thing we can do in performance reports we can't really do in the source code profiler is apply some heuristics to give you some kind of subjective feedback of what is going well or what's not going well. So for example, when the MPI values start to get high relative to compute, we can kind of spot that and give some feedback. Or another one that's actually pretty typical that I think is really useful is memory usage. See a lot of customers running where You're using a pretty low amount of the node's memory, which is often an opportunity to actually run a fewer processes with more memory per node. So kind of a different approach, very easy to detect. So even for just as you're going through, kind of before you dive into the source code, kind of looking at this high level picture. So let me show the illustration of this kind of use case of, so we're going to go through, we start on a Graviton 2, and then step 2 is to add in the ARM performance libraries. So the LAPACK, FFTs, tools like that that have been optimized for ARM architecture. So we add that in, and at a glance here, we can see that the total runtime has gone down some. Good to always kind of scan through the high level metrics, spotting for issues, because as I mentioned, the tool itself will give you some heuristic feedback of things that might be going wrong. So step 2, add in performance libraries. Then we add in a library for doing compression within the HDF file. So Wharf makes heavy use of HDF for doing its I/O, and adding in a specialized library for the compression, we see that we get another good jump in performance. So then at this point, we switch to a Graviton 3. So this has SVE in it, so we're getting vectorization, but we went back to the base Wharf distribution. So even with the base Wharf distribution, Graviton 3 is giving us a nice speed up, and we compare that easily to the base build on Graviton 2. So all things equal, no special optimizations. Graviton 3 is giving us a nice boost in performance. And then we continue through the steps of adding the performance libraries and adding the compression libraries. So just one illustration of how performance reports is a convenient way of doing these kind of configuration level analytics of your application, and being able to look at that at a high level view. And very easy to do with the distribution, so you do not need symbols to create this. So running the release builds directly, you can get this. And on that comment, so Wharf is still the case where you either get a release build or you get a debug build. So when you want to do performance engineering, you have to tweak things and go in and add your favorite optimization to get symbols. With your own codes, I encourage always pretty much using symbols with your optimizations, and that the overhead is super low these days. And a little bit more importantly, even, is if you have a crash of something and it's a non-trivial size, if you have symbols, there's a good chance the debugger can help you find something in the core files where if you did not, it's not very helpful.
Can I briefly interrupt, because we just had a question from Catherine in the chat asking how she can actually get those HTML files from perf report.
Yeah, so when you submit perf report, and let me see if I have a sample here I can run. So Tony had it in the slides of showing kind of the high level perf report as its own command, but I'll just kind of show how to run. So I'm just running directly within my console. So similar to if you have an interactive session. The other approach would be is if you're using a batch file, you would go into your existing batch file and prefix the existing MPI run with perf report. But an interactive session is just perf report. The number of processes.
Hey, Bo, we cannot see your screen, by the way.
Uh-oh. Wonder. Lost the sharing. All right, are we back?
Yes.
And it just runs directly. Uh-oh.
That's always happening with live demos.
Yeah, it sure is. So the
That's what I said.
yeah. So the company got me a new machine, and the Windows machine they got me is about the weakest machine you can get. So it looks like I'm having problems running it, but that is the command line to run it. So there's two options. You can run the command perf report, either directly in a queue or in a batch system. The other approach in the new version, which I mentioned I don't have going yet, map generates both. So it makes it very easy. You can open up the map file from the Forge interface, and you can either look at it as a performance report and save it off as an HTML file or a CSV file, or you can look at it with the native map interface.
Thanks so much for explaining that and trying to do the live demo. I really appreciate it.
Yeah. So usually, so as I mentioned, for both performance reports and map, I encourage the workflow of generate it offline and then come to use the user interface. So I don't actually generate these very often on my machine. Most all the things I'm going to show today, I generated on another machine. Well, let's get to map. Okay, so I'm going to bring up the remotes or bring up the user interface. So connecting on your system, as Tony mentioned, the method I would use, I recommend using is this remote launch. So you can see I have a few machines here that I've configured, which I occasionally connect to, and run the remote launch to connect to your cluster. And then once you've done that, you will be browsing the file system on your cluster. For today, I'm just going to load up some data from my local machine, which was actually generated on another machine, but it's really easy to do that with map files of just, if you have the source code on your local machine and the map files, it's an easy way to view it. So for example, one use case we get quite a bit is at large sites and, large government labs. Folks who want to work on the bus or take their work home, is you can work totally untethered and offline and with the source code and the map files and review those, even though you're not connected in any way to your cluster. Okay. All right, so I'm opening up a file that I've previously generated. And oh, this is not a good one though. I'm gonna choose another one. So the laptop I got is so weak, I can't even really run our tools on here. So I got to choose some files that I created somewhere else. Okay, that looks kind of like it should. So on that comment, by the way, so this is just a toy code that I use for illustrating. And as I mentioned, the user interface and the architecture of map is highly scalable. So I've had the opportunity to run this code on hundreds and hundreds of processes, and everything pretty much looks and feels the same. So obviously the shapes of these curves are a little different when we run at a vastly different scale, but everything pretty much looks and feels the same. So let me go through the user interface a little bit. At the top graph is kind of what I call an activity diagram, where in these charts, the horizontal axis is the timeline of the run, and the vertical axis is the quantity in question. Within the activity diagram, we show about 8 various metrics as kind of a bar chart, where single thread compute is in dark green, MPI is in blue, IO is in orange, cluster would be in beige, GPU would be in purple. I think that's about it. The point is, the chart makes it very easy at a glance to get a sense at a high level of how your program is spending time. So for example, without knowing anything about the source code at all, right away I can tell, okay, there's no multi-threading going on, there's no light green, pretty much all the compute is in single thread compute. There's quite a bit of MPI going on. I think there's a little bit of orange over here on the right, but not much IO, but quite a bit of MPI communication. So thinking back to the performance roadmap, kind of looking for the first issues, IO's typically number one. IO's not much going on here, so not something to worry about just yet. quite a bit of time spent in MPI, so that's probably something that we're going to want to revisit. But let's go through the charts in a little more detail. So underneath the activity diagram, we display various charts. This is just the defaults, but there's about 40 or so various metrics at this point that we gather, and we can kind of go through those. Now within the chart, we can hover over a given point and get quite a bit of information about the run. So for example, at this point, I'm about 2.5 seconds into the run, and floating point ranged from 0% on rank 2 to 90% on rank 7, the mean and a really high standard deviation. And within the chart, we show the maximum, the minimum, and the mean as a solid line. And then the shading around the mean is kind of a variance where the intensity or magnitude of the color is the magnitude of the variance. So really powerful metaphor of getting a sense of the metric across all of your processes. So for floating point, that's another one that might not be good. I mean, we really don't know yet. And as I mentioned on the performance roadmap, we want to focus on first things first. So we'll come back to that MPI. Now in the center pane, source code view, where next to each line of source code, we give a representation of that activity diagram. And you can hover over it and get some details of the breakdown. So for example, on line 10, you can see that about 51% of the time was on line 10 in that call to the imbalance function. And by hovering over, we can see how that breaks down. And then subsequently, for the stride function and the overlap function, we can see kind of occupy the second and third phases of this run. Now at the bottom, kind of a bottom up view, so we can see kind of the thread stacks and drill down within the thread, similar within functions, very similar to gprof, where you would get time spent within a function and the children of that function, which once we've kind of refined our search is very powerful. But I think the main strength is map is using these charts to see how time is spent at a high level across all your processes. And once we've kind of drilled down and done that, using the traditional kind of gprof bottom-up analysis of a function call stack can add to that. Okay, so I mentioned the activity diagram. So IO is fine. We're not going to worry about that, but MPI is not looking so good. So let's bring up the presets for MPI. So these are all of the MPI metric values that we gather. And so MPI call duration, this is looking a little interesting. So let's hover over that chart. Looking underneath, we can see at about 3.6 seconds, it varies from 0 seconds on rank 7 to 3.4 seconds on rank 0 with an enormous standard deviation. So that's not good. Spending 3 seconds in one process, not doing any work is just kind of wasted time that we're not distributing the work in some form. So I'm going to go back to the default and explicitly add in that call duration value. So just in the sake of saving realty, I like to kind of keep the number of charts to 3 or 4 at a time, so we have plenty of space in the source code view to see the source code. Okay. Kind of the core of the technique and map of drilling down and finding issues is through the charts of like looking for patterns where there's potential issues or opportunities within the charts. So we've seen that pattern in the MPI call duration is spending a lot of time idle. So the method of approaching that is highlight that section of the chart. And when I highlight the chart, there's a couple updates that the user interface makes. It updates the time to the left of the chart to only show what I've selected. And then most significantly in the source code view, it only shows the data for what I've selected. So at this point, I can see that 100% of the time for the area of the chart that I've highlighted is in this imbalance function. And then the key to kind of drilling down on that is collapse all of the blocks of code within the source view. And then just block by block, kind of drill down, trying to see what's going on and understand the issue. Now we kind of added, as we're doing that, and we're actually doing computation to the right of the source code view, we've added another pane that gives a little bit of information of how that breaks down. Okay, so at this point, I'm about 3 blocks of nesting in, and I've narrowed it down to the 2 lines of code where there's potentially an issue. And obviously, this is kind of a toy code. It's just a simple calculation, but the workflow for most HPC codes is very similar. You're going to have like 3 to 5 levels of nesting, and then you're going to hit a block where there's a whole bunch of lines of computation. And this workflow of drilling down block by block, kind of studying the different lines and the values to the right of what's going on is kind of the workflow throughout MAP. So at this point, we've narrowed it down to 2 lines of source code. At this point, what I often encourage is using the debugger to study the code. In fact, we've done tutorial sessions where we'll have like, half the folks use the debugger and see if you can find out what the problem is, or just study the code. And even with this trivial code, folks that use the debugger as an analysis tool usually are a lot more fruitful. I'm always kind of harken back. I spent a lot of time on the WRF code and didn't really have tools like this when I did it. And just the time to understand how the code is working. It's very difficult, and using an HPC debugger just to understand the code can be really helpful. But we'll talk about that in the next session. So one other comment here on the lines, and probably notice, is with optimized codes, things will get refactored, and the chart might not always be on the exact line of interest. Especially, I think I did this at an 03 level of optimization, so there was probably quite a bit of refactoring going on. But it's pretty obvious the problem is not on line 87, it's on line 88. So in this case, the code quote error, it's kind of forced, is I'm iterating over a rank number. So I'm not distributing the work across all the processes very well. Okay, so that's kind of the core workflow, and I want to go through one more kind of case in this code to just illustrate how the workflow, whether it's IO or MPI or CPU related stuff, is really very similar within the user interface. So let's go to CPU instructions and see if we can find some areas of opportunity. So just a methodology kind of advice I often recommend is, there's so many metrics that we gather data on. Sometimes a helpful way is to eliminate things that aren't a problem. So for example, in this code, branching is not much branching going on. Integer is very minimal. Integer calculations, inner vectorization, very little, so we can eliminate that. And I know that all the actual calculations in this code are floating points, so that's kind of corroborates what it's doing. One comment on integers, which sometimes confuses people, is branching, switch statements, ifs, whatever, that's integer work. So even in HPC code that's quote all floating points, you're going to have integer work that's going on. So this vectorization, there might be something interesting there. So let's go back to the default. And once again, just manually add in vectorization. Oh, once again, just kind of highlight that section of the chart. And so we can see, so this kind of confirms the floating point that's not going well across that section. Maybe like there's one more in here that I think would be interesting. Oh, and kind of block by block drill down of why it's having slow memory access. And in this case, so we're accessing a Fortran array in row major order. So Fortran stores data column major, C, C++ in row major. And so if we don't get the striding correct, it's going to be cache misses and poor memory access. So this is one of those where, you know, a lot of developers are kind of familiar with that structure in C and Fortran. Maybe not everyone that would be working on it would be. So once again, this is kind of, we really focus on like computation, you know, kind of end user scientists that might not be computational experts. They're more of a science expert of trying to make it easy for them. So in this case, where there's these kind of problems, what I recommend is generate a vectorization report for your run. Go to this section of the vectorization report, and it's going to tell you that you have cache misses and make it a little more obvious of what's going on with the row major versus column major problem. So there was a question about Python, and you guys are doing Python, so I think I want to bring up a Python specific example just to show what it looks like and kind of what the workflow looks like. So with Python, for both performance reports and map, I think the use case is often a focus of seeing that you bolt together your Python stuff such that you're doing the bulk of your time in a library, not within the Python interpreter itself. So for example, a lot of folks will use something like NumPy or Cuppy and then drive that with a Python code, or have a custom piece of Fortran or C that they quote drive with a Python code. Another evolving one is obviously, this is kind of how the whole ML thing is evolving, is the things like TensorFlow and PyTorch, which are compiled code, highly threaded compiled code, but you drive it with Python. I think kind of a large use case in our tools is to see that you are using and piecing together those pieces correctly, because you know a lot of toolkits in Python, see a lot of customers that'll bolt together something like pandas and NumPy, and something gets tweaked wrong and a ton of time ends up in communication or IO instead of the desired computation. So this is one map file and kind of a user story we did of taking a pure Python code that does a dgem, adding in something like NumPy, then adding in NumPy plus MKL and seeing where we can get. So without getting into the code, just to look at the charts again at the top, start with the activity diagram. We can see that the bulk of the time is in single thread compute. There's some phases here where there's some communication going on, and we can get a little more detail about the run. Hit this little icon on the top left about how the run. So we ran with 4 processes. So we'd expect some phases of communication, and we would expect a chunk at the end for a reduction type operation. But the encouraging part is, so this is all driven with Python, but we can hover over the information under the charts and see that essentially 0% of the time is now being spent in Python. And the bulk of the time is being spent in compute. Now, you can see in areas there might be room for a little bit of improvement, but for Python-driven code, to be able to see right away that yes, we piece things together, the actual interpreter is hardly doing anything itself, and we are using the computational libraries and toolkits as we expected. Okay, so Python. OpenMP. So I mentioned we support OpenMP, but my first example did not show that. So we let's bring up something. Okay, here, so. Oh, this is good feedback. So little editorial on the sampler. So as I mentioned, MAP is a sampling profiler. We start out at the order of 50 hertz and we progress in time and resample onto a new base and then decrease the sampling frequency. And that provides really good fidelity for reasonably large runs. My just kind of subjective advice is you want the run to be at least several minutes, 5-10 minutes and beyond will be even better. And so it's just giving me a warning here. I didn't gather a lot of samples, so the fidelity might not be as good as it can, but I just want to show what the data looks like when we're using threading, in particular OpenMP. One other item on that, kind of related to that, is a lot of HPC codes structure is often some startup stuff at the time, loading data, structuring data, setting up grids, that type of work. And then a long phase of computation, and then a phase of output IO, deconstruction type of stuff. A lot of time, you might only be interested in one section of that, probably the computation phase. A lot of codes will use something like HDF for the IO that's already pretty well optimized, and most scientists aren't going to be too interested in that. They're mainly going to be interested in the phase that's focused on computation. And one thing you can do to increase the fidelity more with that is you can tell MAP to not start sampling until you get to the start of that computation phase, and then tell MAP to stop sampling when you get to the end of that computation phase. So for applications where the setup teardown is non-trivial, I suggest taking advantage of that. Okay, once again, starting at the activity diagram.
Sorry,
We can
to
see.
interrupt, there's a question in the chat from Will. He's asking if MAP can also detect neon or SVE usage.
Detect SVE usage?
Yes.
Not exactly, but that's a great question. So these are all x86 codes. I have a Graviton 3 sample, which I can bring up and speak to. And there's a few things with that on Graviton 3, there's some limitations of getting hardware related stuff, and we're working with AWS to improve that. On a general ARM architecture, getting vectorization capability or what was done with SVE is, there's not really a solution out there. And an item that we actually have, we are considering for our roadmap is one of our developers has an idea of how to analyze the code itself and create a model of how the vectorization worked. This would work on x86, but on ARM, there's not really any solutions out there yet, or we haven't found any, and we're looking into that because we think this might be an opportunity to create something to do that. So to answer your question, No, it does not do that on ARM just yet. It's a known problem. We're communicating with both NVIDIA and ARM on our idea. So far, the feedback we get is it sounds interesting and that might be a worthwhile thing to do, and we don't know of a solution that's out there. Okay, with OpenMP, so in the activity
Can I
diagram.
just, before you start continuing, can I ask another question? Because somebody just posted in the chat, can map generate information for a roofline plot?
No, we don't do that. That's another one we continue to consider. So kind of the approach we're taking on is a couple things. On x86, there's great tools for doing that. I think VTune's analysis on x86 is great. No reason to compete with that. On ARM, there's some efforts that are out there. AMD is doing some stuff on their GPU, which we might be able to like leverage. There's also some open source level tools that ARM has done themselves, which I think are somewhat of a solution. So we're certainly considering that. Part of the challenge for us is we don't want to compete with x80 Intel, a VTune type of tool. That's a great tool. Why rebuild it? It's a non-trivial tool to build. On ARM, there's kind of the business challenge of we don't yet really have many customers. I'll be frank with you, you are one of our few customers that are using ARM architecture chips. We're working with Fujitsu, and so there might be some motivation there. We see a lot people, a lot more than we expected in the last several months, showing interest or even commitments to Grace Hopper type of machines. So we certainly have that on our radar of things we continue to investigate and consider. But at this point, we don't have it, and we don't have a firm commitment that we're going to do it.
Okay, thanks a lot.
Anything else on that? Any more questions?
Nope, I can't see other ones.
Okay. Yeah, so in the activity diagram, we can see a whole bunch of time, dark green, single thread compute. The light green is multi-thread compute, and some time spent in MPI. Once again, very similar workflow of just looking for patterns of interest of what's going on. So obviously this has a very significant amount of MPI. So we probably start with MPI or some of the IO things and drill down. But I just wanted to show of how it looks with OpenMP data. So as I mentioned, I have an AWS sample to walk through and show some things with that. But before I do, maybe if we can calibrate how many people did bring a code or bring a map file that they'd be willing to bring up on their machine and talk about it.